You can request someone to leave us another prayer. Vanessa, since your mic is already unmuted, can you help us?
Let's have ourselves for a word of prayer. Father, Lord, we place this day into your hands, Lord Father. We thank you for everything, Lord Father, that you have provided through the rest of the days, Lord Father. Lord Father, as we are beginning this lesson, Lord Father, we ask you, Lord Father, to provide us with knowledge, wisdom, and understanding, Lord Father, so that we can get everything that is going to be held in this lesson. And in Jesus' mighty name we pray.
Amen.
Amen.
Thank you, Vanessa. Okay, so we are going to begin from where we stopped last week. And I remember I left off when someone was asking a question about when do we apply dissociations, and I think that's where we had stopped. And I was explaining, but my battery cut me short, so I'll begin from there. I was talking about equilibria involving hydrogen, iodine, and then hydrogen iodide. And then we said not all dissociations will be treated in terms involving degree of dissociation for calculations. And I explained that when we are applying the degree of dissociation, that means we are dealing with compounds that dissociate to give us products that are direct constituents of that compound. So for example, here we cannot say there was dissociation. There was formation of hydrogen what? Iodide. So in that case, we don't need to apply the degree of dissociation. But if it's the other way around and we have hydrogen iodide giving us hydrogen plus iodine gas, there is a dissociation, and you realize that this dissociation is as forms the direct elements that are forming up this compound. So you realize that we have the hydrogen here and it's being given off. We have the iodide here and it's being given off, like they are direct constituents of that given compound. For example, when we have phosphorus pentachloride, it's also going to dissociate to give us phosphorus trichloride plus chlorine gas. So at this point, we involve what we call what? Degree of dissociation, because you're breaking that compound to give you its exact constituents. And then, of course, if you're having the other way around, you may not need to apply the degree of dissociation because you're forming that compound, so nothing is being dissociated. So I hope that is well understood. So at this point, we had this question. I don't know if people had copied it and had tried it out, because I had requested people to copy it down and try it out. So the degree of dissociation, which we said we represent as alpha, is the fraction or percentage of the original undissociated molecules which have dissociated. So it's basically the degree of the original molecules which dissociate as dissociation happens. So we have an example here. 3 molecules of hydrogen and 1 molecule of iodine were heated together in a sealed tube at 500 degrees Celsius until equilibrium was established. Calculate the number of molecules of hydrogen iodide present in the equilibrium mixture at that. So we say the temperature is usually constant, and then they have given us the equilibrium constant for the reaction between hydrogen and iodine is 50. So that means we have our Kc as 50. So we have the number of moles of hydrogen at initial rate and the number of moles of iodine at initial rate. So that means the number of moles initially for hydrogen, of course, you have to balance the stoichiometric equation. So you have 3 moles initially and 1 mole for iodine. And then, of course, the moles that reacted, since we don't know them and they're the ones actually we are finding at equilibrium, so we will let them be any later. So for example, here we used X. So that means the number of moles that reacted were X and X this side. And since we have 2 moles on the hydrogen iodide, that means you're going to multiply the 2 by the X because you realize that all these are 1, 1. So to balance the number of moles that reacted, we'll have a 2 because it's a 1:2 ratio. Then we'll have the number of moles at equilibrium. We say to get the number of moles at equilibrium, we get the initial number of moles minus the moles that reacted for the reactants. Then when you get to the products, you get the initial number of moles plus the moles that were formed, and you get the ones for the products. So this side we have 3 minus X, which gives us the moles at equilibrium. Then we have 1 minus X, which gives us the moles at equilibrium for iodine. Then we have 0 plus 2X, which gives us 2X as the number of moles of hydrogen iodide at what? At equilibrium. So remember, we've been given the Kc constant. That means, who can remind me how we can find the Kc? Which formula do we use to get the Kc for this reaction? Anyone to raise their hand and they tell me what to do? Okay, I'm not getting any responses. I don't know if people are still thinking through. So we have Kc is equal to the constant. The appropriate powers on these ones are ones, so we may as well ignore them. So you're going to feed in the values. You'll have 2x squared out of 3 minus x times 1 times minus x. And this is equal to 50 because our Kc that was given to us is 50. And then, of course, you work out and solve the value of x at that point. And then remember, they asked for the number of moles of the iodide, of the hydrogen iodide at equilibrium. Remember, we had 2x as our number of moles at equilibrium. So that means the value of x you get, you're going to multiply it by 2 to get the actual value that you're looking for. So for those who tried out, which answer did we get? And like we said last time, when you get the values of x, you have to look at the number of moles that you're working with. So in this case, we have two values of x. We have the 3.384 and then 0.964. So we said we can't choose the one that exceeds the number of moles that each of those components has. So in that case, we'll take the one that is smaller because it can accommodate the number of moles that can react at any given level. So in that case, like I said, you get since we had 2x uh, as our moles at equilibrium, that means you get 2 times the value of x to give us 1.938 moles. So basically, that is what the calculation was about. And you'd easily get your values. And then they are told us to to describe the experiment that occurs at that point. And remember, when we're looking at the experiments of Kc, we talked about the one for hydrogen iodide. And we said in that case, we use potassium, we titrate against sodium thiosulfate using the starch indicator. And of course, the equation is required for the reaction between the iodine and the what? And the thiosulfate. And then you're able to get the iodide ions and then the thiosulfate ions. So are we all together up to that point? Sorry about that. Someone called my phone and I went off. So I was still asking who can share with us some of the characteristics they remember about chemical equilibrium reactions. We looked at four of them. So if you can remember at least one, you can share your answer in the chat or you can raise your hand and you tell us. Yes, Gilson. Candidates, can we please respond? They are reversible. Thank you. That is good. Any other?
The reaction should occur in a closed system,
Very good. Thank you.
and the temperature should be constant.
Okay, good. Any other? The fourth one?
And
Anyone?
the rate of
Okay.
the forward reaction should be equal to the rate of the backward reaction.
Okay, very good. Thank you so much, Gilson. And the person in the chat, I don't know which name you called by, but thank you. So we said these reactions, first of all, they are reversible. The temperature should be constant and the experiment should be carried out in a closed system. So you realize that even when we're explaining the experiments, they were always talking about breaking the tube in a closed breaking that tube to maintain the what? The equilibrium. So that means you have to carry it out in a closed system so that the outside factors do not affect the rate of reaction. And then also we say the rate of forward reaction should be equal to the rate of the backward reaction. That is why we have them as reversible reactions so that we can establish the what? The equilibrium. Please always remember those characteristics that will help you work well with these calculations. Then part B says 25 moles of hydrogen and 18 moles of iodine vapor were heated in 1 liter sealed tube at that temperature. When equilibrium was attained, the tube was rapidly cooled and found to contain 30.8 moles of hydrogen iodide. Who can give us the reason why the tube was rapidly cooled? Anyone to tell us why you think the tube was rapidly cooled? Like I said, you can always share your thoughts in the chat or you raise your hand and tell us. Yes, Wilson.
The tube was rapidly cooled to stop the reaction and fix the equilibrium such that it does not adjust itself to any other equilibrium value at a lower temperature.
Okay, that is very good. I can't say any better. So you realize that that tube was cooled rapidly so that we could establish the equilibrium and so that the temperature would not go below the one we are expected to have at obtaining the equilibrium. So you're supposed to do that very rapidly to ensure that you attain the equilibrium that you need at that particular time. You need to establish the equilibrium at a specific temperature. So the temperature should not go lower than what you expect to obtain at what? At equilibrium. And then the second question is telling us calculate the value of equilibrium. Okay, so I just wanted us to have the statement here. A tube is rapidly cooled to stop the reaction, first of all, and fix the equilibrium such that the equilibrium does not adjust itself to the equilibrium value at a lower temperature. Please take note of those underlined words. They are very important for you to have them in your statement. So first of all, it will stop the reaction. Then you'll fix the equilibrium. And then the equilibrium will not adjust itself to the equilibrium value at a lower temperature. So we have our calculation here. Calculate the value of equilibrium constant for the reaction taking place in the flask and the degree of dissociation of hydrogen iodide. So in this case, remember we have, so that means our first part, we are finding the Kc. So that means we are having hydrogen reacting with the what? With the iodine to give us hydrogen iodide. And then the second part of the question is telling us we need to find the degree of dissociation of the hydrogen iodide. That means after finding the Kc, you're going to find the formation of, the dissociation of hydrogen iodide. This time round, you are forming it, but when you're finding the dissociation degree, that means you need to dissociate the hydrogen iodide in order to give you the what? The degree of dissociation. And for those of us that were around during that experiment of the dissociation of hydrogen iodide, the formula that we used there is the same formula we adopt at this point. But still you can work out and still get there if you don't remember the formula. So should I give us some 3 minutes to try it out and then we can share together? Okay, so let's try it out. At 30 minutes past 1, those that have gotten answers can share in the chat so that we know what to work with. But please, candidates, let's respond. It helps me work better. You know, when you're teaching a class that is participating, there is a flow. But if people are quiet, you seem to ask yourself if you're teaching yourself or something. Okay? So let's respond. At least use the chat to notify me, raise your hand and speak up. It's a good thing. Eh? Yeah, thank you. Okay, Gilson, that's good. Thank you. Let's get responses from the rest as well. Okay, thank you, Vanessa. So it's 1:30. I think we can do this together. And since we've got some responses, the rest of us can follow through as we work out. So what is going to happen here is we have 25, we say we have 25 moles initially of hydrogen and 18 moles of iodine initially. And that is what is related here. And of course, initially at the formation of hydrogen iodide, we have 0 moles. And then the moles that reacted, we let them be any later. So X, and then since we have a 2 here, so it becomes 2X. And then of course, you'll have the initial moles minus the moles that reacted to give you 25 minus X, and then 18 minus X. And then side, remember the question gave us the number of moles of hydrogen iodide at equilibrium. So that means the number of moles of hydrogen iodide at equilibrium are 30.8. So the 30.8 can help us to find the value of X because 2X is equal to what? To the 30.8. Because remember, originally, if we had not been given this value, we would have said initial moles plus the what? The moles that reacted, and those are the moles that would have at equilibrium as 2X. So that means those two values are equal to each other. And then it will help us get a value of X, which is 15.4. And of course, since we have the value of X, we can find the value of this and that by subtracting. So in that case, we'll have the value of the number of moles at equilibrium for hydrogen as 9.6 and for iodine as 2.6. And then we are able to get the Kc as the concentration of the product over the product of the concentrations of the reactants to their appropriate powers. And of course, when you feed in, you'll be able to get your Kc as 38 point some values, which most of us didn't round off, but the value of Kc at that point would be 38. So when we are finding the degree of dissociation, like I said, so this time around, we are going to have uh, our hydrogen iodide dissociating to give us hydrogen plus the what? Iodine gas. So at this point, we are going to establish the degree of dissociation. So if we have the number of moles that reacted, the initial number of moles as maybe, we can use maybe, M, and then we say, we have M this side, and then the number of moles this side would be at the point of formation, they are that. And then of course, when you get to the number of moles that reacted, that's when the dissociation comes in, the dissociation degree. And we say the degree of dissociation is represented as alpha. That is where you find that you have M alpha. And then this side, since we have 1 mole, yet the number of moles side is 2 to 1. That means we'll have M over 2 dissociating, and then M over 2 dissociating. So at that point, the degree of dissociation for hydrogen and iodine are the same because they are all to 1 ratio. And then, of course, we'll carry the method. We use the other side of the experiment to find the degree of what? Dissociation, alpha. And of course, we know since we have the Kc here as 38, that means for us to get the Kc for the dissociation, we'll have Kc is equal to the concentration of hydrogen and the concentration of iodine, because this time around they are the products, over the concentration of the hydrogen iodide, which is 2. But remember, this one is a reciprocal of what we have here. So that means if the Kc was 38, this time if we get the inverse of the Kc, it will become 1 over 38 is equal to the concentrations we have this side to give us the value of what? The degree of dissociation. So like, for example, what we have here, we have P as the initial number of moles and then 0 this side and that side. And then of course we have the degree of dissociation as C times the alpha. And then, like I said, since it's a mole ratio of 2 to 1, we divide by 2 on the products. And then of course we have the initial number of moles minus the number of moles that were formed, and then this side the dissociation moles plus the original moles that we had. So in that case, when we are getting the concentration, remember, for us to have concentration, we have the number of moles over the volume. So in that case, you will have divided by V, divided by 2V, divided by 2V. And then you'll come and feed into the formula. And if you can recall, this is the formula we had established in the experiment. And then, since we have the Kc, we use the reciprocal and get 1 over 8 is equal to what we have this side. And then, of course, you use the quadratic equation formula to find the value of alpha. But remember, alpha cannot be negative. The degree of dissociation can't be negative. So we discard the negative value and we take on the positive value to become our degree of dissociation. Are we all together up to that point? Okay, thank you. So we have another question here, and I want us to first try it out. And this time, this question is about Kp. So I want us to first try it out, depending on the explanation I gave us the other time, but we need to get the partial pressures, and then we insert them into the formula. So let's first try it out, and we can share our answers in the chat, and then we can build on from there. I'm going to give us 5 minutes to try out and see. So the question is saying, when stoichiometric amounts of hydrogen and iodine are allowed to reach equilibrium in a 1-liter vessel at 450 degrees Celsius and 1.01 times 10 power 5 newtons per meter squared, 1.56 moles of hydrogen iodide were formed at equilibrium. Calculate the equilibrium constant, Kp. So remember, the only areas where we apply Kp is when the question has specified that find the Kp, or when you have pressures given to you, or when you have gases only reacting and they have given you their different partial pressures. So in that way, you can apply the Kp method to get the constant, the equilibrium constant of those reactants. So let's try it out, and then at 143 we will share what we have. And if you get the answer before 1:43, you can always share in the chat and we build on from there. Wow, Hilson, you're quite fast. Thank you. I don't know if we have some other people who are trying out these numbers. Please let's try out numbers. It helps you understand better. At least let's have 3 people post by 1:43 so that we can, or even more. All the 20, all the 20 students that we have can share, unless we have some that are not offering chemistry, but they are here. But otherwise, if all of us are chemists, then we can try out and share our findings. Because if you understand the calculations, then that is basically it about chemical equilibria. You can actually just share, and you know that if you go to the QB, you can attempt any number on chemical equilibrium. Like I presume some of us have already done that by going into your question bank, you try out some numbers. Okay, so it's time up, so we can try out the number together. So in this case, they gave us they say when the stoichiometric amounts of hydrogen and iodide were allowed to reach equilibrium in 1 liter vessel at that, and we have 1 point that as the pressure, 1.5 moles, 0.56 moles of hydrogen iodide were formed at equilibrium. So we have the number of moles of hydrogen iodide that were formed at equilibrium. But our initial number of moles for hydrogen and iodide are 1 to 1. And then, of course, the initial number of moles of hydrogen iodide are at 0. And then, of course, we'll let the, thank you. I don't know this person who is using an exclamation mark and question mark because you're not using your name. So it's hard to identify who you are. But thank you for your feedback. So, of course, we are going to let the number of moles formed, all those that reacted to Bx. And then we'll have, thank you, Gina. And then we have, sorry. Okay, so like I was saying, we'll have 2x, and then of course we have the number of moles here as 1 minus x, and then 1 minus x, and then we have plus 2x. So in this case, we'll have 1 minus x as our moles at equilibrium, 1 minus x as our moles at equilibrium. But since the number of moles at equilibrium are given to us here, that means we are going to have 1.5. And like I say, since we have 0 plus 2x, so those two moles equate to each other, and then we get the value of x. So after getting the value of x, which is 0.78, we'll have the total number of moles. The total number of moles we'll have attained here at equilibrium. We have this plus the ones of 2x. So we'll have 1 minus x plus 1 minus x plus 2x. So this gives us 2 moles. So that means those are the total number of moles at equilibrium. And then, of course, we said when we are getting the partial pressure gas, we'll have the number of moles at equilibrium, which is 1 minus x, divided by the total number of moles at equilibrium, and was the pressure that was given to us, the pressure at equilibrium, which is 1.01 times 10 power 5. So that is how basically you had to calculate the partial pressures. You get the moles at equilibrium over the total number of moles at equilibrium times the pressure at equilibrium. And then it's able to give you 1.11. And then the same thing happens for iodine. And then you get the same pressure. And then the same thing is happening for the hydrogen iodide, which gives you this as the pressure of hydrogen iodide. And then in that case, of course, say Kp differs, reason being we use, I don't know, do we call these curly brackets, non-square brackets? So in this case, you have partial pressure of hydrogen iodide to its appropriate power times the partial pressure of hydrogen times the partial pressure of iodine, sorry. And then you're able to feed in the partial pressures, and then it gives you the Kp of 50.28. So all those who posted their findings, and even those who haven't posted but you tried out, congratulations and bravo. Ochero, was it a typing error of 58.28, or that is what you actually wrote? So like we said, in case C, the C is a subscript. Even in P, the P is a subscript. Please always take note of that as you're writing your answers. So are we all together at that point? So now at least we started on the calculations that show the Kp. So you will have Kc and then Kp. So today basically we'll focus our focus on the our focus will be on the Kp. So there is another question for us to try out here. So we have the equilibrium constant for the dissociation of hydrogen iodide is 0.02. 1 mole of hydrogen and a third moles of iodine were heated together at 450 degrees Celsius. Calculate the mass of hydrogen iodide present in the equilibrium mixture. So here we are finding the mass of hydrogen iodide that is being used in the equilibrium mixture. Okay, good enough. I don't know, Gilson, where the clarification should be done, but let's first try out this number. Then maybe as we are going through it, I can throw more light, and where you're not able to get the point, you can still ask a definite question on where you need clarification on the degree of dissociation. That is okay. So I'm going to give us up to 155. 155, we'll go through the number and then I'll draw more light on the degree of dissociation. Thank you, Gilson. And uh, okay, now it's time out. I think we'll just have to go over the question together. So we have we have equilibrium constant, like I already said, when they give us the initial number of moles, it becomes easy for us to substitute them where they belong. And of course, if we don't know the number of that were formed or those that reacted, we denote them with any letter. You don't restrict yourself to X unless it's the one you actually feel comfortable with. Then the number of moles at equilibrium are 1 minus X, and then 1 over 3 minus X, and then we have 2X. But remember, in this case, the number of moles that were given were the ones for the formation of hydrogen iodide. So we can find the Kc using that given value. But of course, something you need to note is they've given us the equilibrium constant dissociation value. So we have the equilibrium dissociation value, which is 0.02. And we said the other time that when we are finding Kc of the reaction, of this reaction, it's the same as the inverse of the Kc of this reaction going backward, where you have the forward reaction giving you the Kc, while going back, we have the dissociation, the degree of dissociation where the hydrogen iodide is splitting into hydrogen and iodine to give us 1 over Kc. So in that case, we adopt the other formula which we had initially, where we had hydrogen iodide squared divided by hydrogen. Now these are square brackets, sorry, because we are dealing with concentrations. So you will have this, and then you have iodine. So in this case, you have 2x squared, like we have here, and then we have this value and that value as written in the brackets. But then the degree of dissociation, the case of the reaction is as a result of 1 over the Kc for dissociation for the what? For the hydrogen iodide. So in that case, it will help you find the value of X. And of course, we choose the smallest value of X because I said you look at the number of moles that we have. They're the ones that actually help you generate what value of X you're going to choose if you have 2 values of X. We can't choose a value that is bigger than both values. And then you will have the moles at equilibrium by multiplying by 2 to get the value of X. And then the molar mass, of course, we know that the mass of hydrogen is 1, while the mass of iodine is 127. And then you get the 1,8, and then of course you'll have to multiply the moles at equilibrium times the molar mass in order to give you the what? The mass at equilibrium. So about the degree of dissociation, one of the things you need to take note of, like I said at the beginning of the lesson, when you're looking at degree of dissociation, which is alpha, the degree of dissociation comes in when you are obtaining individual elements or individual components that are from that exact compound that you're working with. For example, I say if you have hydrogen iodide, you realize that it's giving you its constituent elements. You have the hydrogen and you have the iodine. And I also gave another example where you have phosphorus pentachloride to give you phosphorus trichloride plus what? Chlorine gas. So you realize that this compound is directly obtained from here. The same thing happening from what? So you're splitting a given compound into its constituent compounds or elements. So in that case, it gives you the feel of what the degree of dissociation is. And like we say, the degree of dissociation is the amount of particles of the undissociated compound forming its dissociated what? Elements. So for example, here, the degree of dissociation, since it's a ratio of 1 to 1, you realize that you will have the degree of dissociation of phosphorus pentachloride as alpha, and then you'll come decide it will be alpha, and then decide it will also be alpha, depending on the number of moles you have initially, so that you subtract to get the number of moles at equilibrium. It will always guide you on what to do. But degree of dissociation comes in when you're splitting that component to give you the exact things that make it up. For example, when you're cutting a pineapple, you don't expect to get pieces of mangoes from it. So that means you get smaller pieces of what? Of pineapples from that pineapple. So it's the same when you're dissociating. It gives you the exact, and you realize that dissociation is happening when you have one compound splitting into its variant components, which is not the case when we're doing the esterification of the ethanoate. So that is something you need to have at the back of your mind, that when you're dissociating, you get the constituents of that compound that has been given to you, and you're able to get the degree of dissociation depending on the number of moles. And then also the other thing about this question, when we are given the degree of dissociation, we can find the Kc of that reaction by getting 1 over the degree of what? Of dissociation that has been given to us. So for example, you can see that we are equating the reciprocal of the degree of dissociation to what we would have expected to get this side as the Kc. So, and then you're able to get the value of what? Of X. I don't know if I am making sense at that point. Yes, Gilson.
I think should I just like post the now we have got the case here as alpha squared divide by 4 into bracket 1 minus alpha into bracket squared. Now, should I just need to get that formula in the head, okay, without calculating it, and I paste it on the, okay, before like the other parts, should I just calculate it? Should I just paste it without calculating it, then I do the rest of the calculations?
Oh, I didn't get your question. At what should you paste? The Kc?
Yeah, the case, like not calculating it, starting from this side of initial moles reacted, moles at equilibrium. Like you just write it, then you find the degree of dissociation.
Now, that would have been okay, but remember, this is part of the working. So if you don't have these initial states, we do not know where you got your values from. I don't know if I am answering your question. So you will need to have the working to show us where you got the moles that you're using in the Kc. Are you getting my point?
Yes.
So for example, this question, they have given us the degree of dissociation, and maybe something that comes to our minds on this question is that Kc can also be found when we have the degree of what? Of dissociation. So that means the degree of dissociation, because now in this question, we are forming hydrogen iodide. But the degree of dissociation comes in when we are splitting hydrogen what? Iodide. That's why we are saying that Kc is equal to the inverse of the what? Of the degree of dissociation. But you notice that we carried our Kc, which is this one here, because we are forming hydrogen iodide, which is our product, and then the reactants. But then we also can find Kc by saying Kc over reactant is 1 over Kc for the dissociation of hydrogen iodide. So you will have 1 over the what? over the degree of dissociation that was given to us. But now you're carrying this component here to equate it to the Kc. So these variables here, we need to see them in your working, how you obtain them. Because you see this 1 minus x is what we have here. 1 over 3 minus x is what we have here. 2x is 2x squared. So Gilson, have I answered your question?
Yes, teacher, I'm trying to relate now.
So basically, that is what you need to understand about the degree of dissociation. Just need to have the feel at the back of your mind that if I'm given, because that is why we are trying out different examples. Someone may say, why are we doing many examples? But these questions come in different forms. So for example, you may never have imagined that you can find Kc by having the 1 over the degree of dissociation. And of course, you'll appreciate this more as you look at ionic equilibrium at school and many other topics that will come thereafter. But as you read the question, you start to understand that there are different ways I can find the degree of what? I can find the equilibrium constant and how I can play around the information that has been given to me to extract what the question actually wants. Okay, so for the people who are joining us for the very first time, please, the recordings are there on YouTube. You can go and watch them so that you can follow through. Otherwise, I don't think this topic is so hard if you really give attention and try out the different numbers that we have. Okay, so should we proceed? Should I take that we are all together and we proceed?
Yes, teacher, you can continue.
Okay, thank you. So we have another number here on partial pressures. It's saying 1 gram of hydrogen and 127 grams of iodine are allowed to obtain equilibrium in an evacuated container of value 10 decimeters cubed at a temperature of 450 degrees. Evacuated, sorry. If the equilibrium constant at the same temperature, Kc is 50, calculate the value of Kp, the total pressure in the container, and then the partial pressure of hydrogen in the container. So as always, let's first try out and then we can post our answers in the chat. At 3 minutes, sorry, at 1:13, this we should be able to go on. So let's first try out and see what we get. Asking the chat, do we have something like degree of association? Yes, we do. And I think in inorganic chemistry, you if you've not yet reached there, you look at some of where we have the degree of association. But for this chemical equilibrium, because remember we talked about the reversible and irreversible reactions. So we said we only focus on the reversible reactions. And because we are looking at splitting the what? The given compound, we really focus more on the degree of dissociation at this point. Thank you, Ms. Palmer. I don't know if that's a pronunciation of your name, but thank you. May you clarify what you mean by DN? Sorry, I didn't notice my microphone was muted. Sorry about that. Okay, I was saying, thank you all for your responses in the chat. So I was saying we have the molar mass. Of course, molar mass is 2 grams, and then for iodine is twice the atomic number, sorry, the atomic mass, and then you have 254, and then of course the mole ratio between hydrogen and hydrogen iodide is 1 to 2, and the number of moles of hydrogen iodide are 2 times 0.5, which is equal to 1 mole. Because remember, if the mole ratio is 1 to 2 and the moles for hydrogen and iodine are the same, which is 0.5, we multiply them by 2 to give us 1 mole. And we're given the Kc, we're given the gas constant, and then the volume, which we converted to meters cubed. And then remember, all these are supposed to be in standard values. So because of the R, we have to convert this into meters cubed, because remember, this R applies when we have newtons per meters what? Squared. So that is why we need to convert the volume to meters cubed so that it can rhyme with the R that we have. And then the temperature, of course, it's supposed to be in Kelvin. And then the difference in number of moles, we said we get the number of moles of the product minus the sum of the reactants. And since the reactants have 0.5 plus 0.5, which is 1, 1 minus 1 gives us what? 0. So that means our difference in number of moles is 0. And we said when we have Kp, we say Kp is equal to Kc brackets RT to the power of the difference in the number of what? Of moles. So we're given the Kp, sorry, we are looking for the Kp, we're given the Kc as 50. We have the R, we have the temperature. And then to the power of the what? Of the difference in the number of moles, which gives us what? 50. So if you got that, bravo, and you can clap for yourself wherever you are. And then for those who hadn't tried out, please, that is how you would go about this number. You get all the given values in their standard forms, and then you're able to feed into that formula, which we extracted the other time. So if you don't know how we came about this formula, you can go back and watch the previous videos to know how we got that. And then, of course, we have then, of course, we have to find the total pressure in the container. And for us to obtain the pressure in the container, we need to get the different pressures that are required at that point. So we have the initial moles, which are 0.5, 0.5, and these are 0. Then the X, and then that part. I am sure now most of us are champion that part of finding the initial moles, the moles that reacted, the moles that formed at equilibrium. So for us to get the moles at equilibrium for the mixture, we said we add the moles that are occurring at equilibrium, and that is going to give us 1, because we have 5.5, which is 1, and then the X's cancel to give us 1 as the value. And then since we have the number of moles at equilibrium, that means we can feed into the formula of PV. PV is equal to nRT. nRT. So we have we are looking at pressure, we have the volume, we have the number of moles, we have the R, we have the T. So it means it can help us get the pressure. And I saw someone posting it in the chat. So you feed in those values and you're able to get your pressure at that point. Then they also ask for the partial pressure of hydrogen. So to get the partial pressure of hydrogen, of course, you're going to first find the value of X, so that you can get, because we said partial pressure of hydrogen is equal to the moles at equilibrium for hydrogen over the total number of moles at equilibrium, and then times the what? The pressure, times the pressure that you have at that point. So that means you're going to use Kc, and since you already have your Kc, you're going to have it as 50 is equal to the concentration, the number of moles of concentration of hydrogen iodide squared divided by the number of moles of hydrogen and those of iodine, and then you're able to do the math. Then you choose the smallest value of x, and then in this case, you realize that we have two values, which is 0.697 and 3. Because we said we can't get negative moles. That means we can't use this value because it's bigger than the moles that we have initially. So that means when you subtract, you'll choose the bigger number of moles, the smaller number of moles, and then you subtract, and then you're able to get those values. And I think I saw some of those as well. Did we all get to that point when we're calculating? Anyone who found issues that needs clarity on a given part? Are we all?
Yeah.
Okay, thank you. So you get your partial pressure of hydrogen as that. So we have another question here, which is saying 3.20. We have 3.20 grams of hydrogen iodide were heated at 450 degrees Celsius in a glass bulb of volume that, when equilibrium was attained, the bulb was rapidly cooled to room temperature and then broken under a solution of potassium iodide. The iodine formed required 36.0 degrees Celsius, sorry, 36.0 centimeters cubed of 0.2 molar sodium thiosulfate solution in the presence of such indicator for complete reaction. So I would want to hear from us before we begin calculating. Explain why the bulb was broken under potassium iodide solution. Who can tell us why they think the bulb was broken under potassium iodide solution? Anyone who has an idea? You can post your thoughts in the chat, or you can raise your hand and you tell us. Why do you think this bulb was broken in potassium iodide solution? Yes, Gilson?
I think to dissolve the the chlorine, I think to dissolve the chlorine and the chlorine reduced to the chloride ion and oxidized to iodine. I think I can't get it well, but actually.
Okay, you are on the right track, but I don't know where you're getting chlorine from. Maybe you can tell us where the chlorine comes from. Because I think your explanation is valid, but you need to improve it. I don't know where the chlorine is coming from.
Sorry, I was thinking it the other. I think of chlorine, but I need to dissolve the iodine present, I think.
Okay, thank you. So when we're looking at the experiment, we said we break it under potassium iodide because we expect the iodine produced at equilibrium to react with the what? To be dissolved in the potassium iodide so that we can know, in the potassium iodide, so that we can know the iodine that was existent in the tube at what? At equilibrium. So let's see what we have here. So it's saying the valve is broken under an aqueous solution of potassium iodide to dissolve the iodine present at equilibrium. Okay, thank you, Miss Kauma. Potassium iodide was used to dissolve iodine and in the cold media to prevent shifting of the equilibrium position. That's good. It's just a different phrasal, but it's the same thing. So thank you. So when finding the equilibrium constant here, what are we finding? Are we finding the Kc or the Kp? Who can tell us which equilibrium constant we are finding in this question? According to the question, which equilibrium constant are you finding? Kp or Kc? Okay, someone is saying Kc. Can you give us a reason why you think we are using Kc and not Kp? Okay, maybe as we look through, of course, we are going to use Kc here because we have been given the masses and the volumes and then the molarity. So that means in that case, we have no way we are going to apply the partial pressures. So it's better for us to stick and look at what? At K, at Kc. So maybe briefly, I want us to copy that question plus this question here. Please don't xerox the answers as yet. First try out. The degree of dissociation of 0.5 moles of hydrogen iodide was found to be 25% at a certain temperature in a 1.5 decimeter vessel. Calculate the equilibrium constant. Yeah, that's true, Christina. Miss Kauma. I don't know how your name is pronounced, so I don't want to, if I am mispronouncing it, sorry, but you need to teach me maybe how to pronounce it better. So let's copy this question as well, plus the first one. I'm going to go back to the first one I showed, but let's copy this one as well. The degree of dissociation of 0.5 moles of hydrogen iodide was found to be 25% at a certain temperature in a 1.5 decimeter cubed vessel. Calculate the equilibrium constant Kc. So I don't know how many of us can take a screenshot because I requested Parlison to begin early because I have some other things I really need to work on. So I wanted us to take a screenshot. So I don't know how many of us can take a screenshot, at least to try out these questions. In case this is our last lesson, you can always keep trying out. Of course, sending that document really takes me quite some time to compile those things, which I will try to do. I can't really promise because it seems I've overpromised, and but I'll try to put those questions together so that we can have them. Juliet, your hand is up. Do you have a question?
Yes, madam. I'm
Yes, please.
requesting you to explain to me why the bulb is broken under potassium iodide. I had not understood the explanation.
Okay. Can someone explain for Juliet what we said, why the bulb is broken under the bulb of potassium iodide? Yes, Paoma?
Yes, teacher, I think iodine can easily dissolve in potassium iodide than any other solvent. So meaning that we preferably use potassium iodide for dissolving iodine, and then two, we prefer dissolving it at cold conditions to ensure that you do not have shifting of the equilibrium position, so that you maintain the concentrations of the reactants and products at a given time. You maintain them.
Okay, thank you, Paoma. That is good. So basically, you have to look at the fact that because every time you're choosing to break a substance in a given solution, that means it can easily dissolve in that solution. And it also helps us to maintain the equilibrium the same way it was initially before the what? The breaking of that tube. So that is why we are keeping it there. And because iodine is going to dissolve in the potassium iodide, it's going to help us establish the equilibrium for the rest, because if we have the equilibrium concentration of iodine, it can easily give us what the rest equilibrium was. So it is basically that. I don't know if that makes sense, Juliet. Yes, Ambrose?
It does.
Okay, assuming like the tube was broken in a potassium iodide solution, so as to stop the reaction and fix the equilibrium such that it not adjust itself the equilibrium value at temperature.
Ambrose, you're breaking. Is it possible to attend on network?
Okay, I'm like the was broken. The equilibrium does not adjust itself to equilibrium temperature.
If someone is speaking what Ambrose is asking, can you please help me re-echo it so that I can know what his question actually is?
Okay, madam.
Yes.
Madam, can you hear me now?
Yeah, that's much clearer.
Okay, let me just put in the chat.
Okay, but now you're clear. So maybe you ask, if I can't get you, then you can post in the chat. But for now, you can talk.
Okay, like I was saying, assuming I answer that question in this way, like that the potassium iodide solution, the tube, okay, the tube is broken in potassium iodide solution, so as to stop the reaction and fix the equilibrium such that the equilibrium does not adjust itself to equilibrium value at a lower temperature. Can it make some sense?
Okay. Yeah, it does make sense, but does your question involve the word dissolving the iodine at that specific equilibrium? Because much as it's not going to shift the equilibrium, which is good, but it also has to dissolve the iodine. That is the main reason why we are actually using it.
It's okay.
Okay, but otherwise, the explanation is good. So, there are quite some questions here, which are quite many for us to try out, but I'll see how I can get them across to us. So I request us to stop here for today. You can try out those two numbers for now. And if we are not able to meet again, you are an amazing class, and thank you for always connecting in. And if you have any questions, you can always feel free to let us know, and we can help where possible. So I'll request someone to pray for us in closure, and then we can begin from there if we happen to have another lesson this holiday or next holiday. Anyone to pray for us? Paloma, your hand is up. I don't know if it remained up, but you can as well close for us in prayer. Hey, candidates, no one wants to pray. Or is it that they just want the lesson to go on and on and on? But I told us I don't want to just blank out. I just want to close the lesson in a better way. Yes, Ambrose.
Okay, let's humble ourselves and we pray. Heavenly Father, I want to say thank you for today. I want to say thank you for the wonderful lesson we have had. Pray that may you continue guiding us, protecting us, and imparting to us direct wisdom, knowledge, and understanding, so that we shall always continue prospering. I want to pray all this believing that your word in Jesus' name I pray.
Amen. Okay, thank you all. Have a blessed weekend.
Okay.
Okay, I'll send the work on, I'll give Mr. Kasiba the work, and they will share on the group. So endeavor to try out those numbers. Okay, so
okay,
in case we are able to connect next week, which topic can we look at? Because basically the remaining part is about calculation.
Maybe we can look at people are suggesting from the chat. Guys, I think the teacher has left. Okay, some people are saying face equilibrium.